Hello there. In this video, we're going to talk about L'Hopital's rule and specifically the quotient indeterminate forms only. This is the AP Calculus topic 4.7, if that matters to you. And if you are a random passerby on the internet and you want to print the guided notes sheets that I give my students, you can go to this bit.ly link down here to do so. So, excuse me, let's talk about L'Hopital's rule and remind you what indeterminate forms are, or teach you what they are. Maybe you didn't know what they were to begin with. But when we are in the world of limits, the two most common indeterminate forms we will deal with are when your limit yields 0 divided by 0 or infinity divided by infinity after your initial substitution or analyzing step. Now, I tell my students that if you do have a limit that is in indeterminate form, all that means is that you need to do more work. You cannot look at 0 over 0 or infinity over infinity when it comes to limits and simply know the answer by looking at those two things alone. We have to analyze the function in a little bit more detail to figure out what's happening. And keep in mind that the 0 over 0, we say that, or I say that kind of lazily. But remember, in the world of limits, it's things that are getting close to 0. We're not actually at 0, we're approaching 0, and the final answer depends on how quickly the numerator and the denominator are approaching 0 relative to each other, and that is what L'Hopital's rule will allow us to analyze. Now, before we learned L'Hopital's rule, my students were told that do more work means do some level of algebra, factoring, conjugates, something else, until you can cancel or divide out a factor that was the source of the zeros, and then once you divide that source of the zero out, you usually can plug back in to get your answer. So let's look very quickly at some algebraic techniques that you can use for limits. And here, if you look at the numerator, 4 squared minus 16 is 0, 4 squared minus 5, 16 minus 20 is negative 4 plus 4 is also 0, so we do need to do more work on this one. And again, this is just a quick review of the algebraic techniques. This one I'll probably factor x plus 4, x minus 4 in the numerator. Denominator, there'll be x minus 1, x minus 4, and here is what I was looking for. I need to divide something out. Those x minus 4s will divide away, and at that point I can substitute 4 back in for all remaining x's, and we get 8 over 7, 8 over 3 for the answer to this one. X minus 1. Yeah, that's all right. And then for number 2, x is going to infinity this time. And initially you can look at that and say that's approaching infinity, and so is the denominator. But infinity over infinity, that is also an indeterminate form. Now, if you're really good at memorization of rules, your bottom degree is larger, and if your bottom degree is larger and x is going to infinity, then the answer to the limit will be 0. The other trick, in order to work that out a little bit more mathematically, would be to divide every term by the highest power of x in the denominator. So I'm going to divide by everything by x squared, and when I do that, I get the limit as x goes to infinity of 3x over x squared is 3 over x, 1 over x squared over x squared is 1, and 9 over x squared is 9 over x squared. And now I have 4 separate things that I need to look at, really 3, because I only have 3 expressions that still have x's in them. And in the world of limits, if your denominator is infinitely large and you have a constant on top, all of these are like 3 over infinity, 1 divided by infinity, 9 divided by infinity, all crash to 0. And the answer to this limit would be 0 plus 0 over 1 minus 0, or 0. Now that's obviously the longest way to work it, and even after L'Hopital's rule, it's definitely more efficient for you to remember those degree rules, but L'Hopital's rule does give you an option if you forget those. So I've mentioned L'Hopital's rule enough, so let's talk about L'Hopital's rule, and L'Hopital's rule can only be used if your limit is in your quotient indeterminate form. There are other indeterminate forms. There are product indeterminate forms of 0 times infinity. There are exponential indeterminate forms. But in this video, we're going to talk about quotient indeterminate forms. And even in those other forms, before you apply L'Hopital's rule, you have to use some algebraic type technique to turn it into a quotient before you can apply L'Hopital's rule. So let's talk about what L'Hopital's rule is. And it starts by knowing that the limit of f and g each on their own approach 0. And if that is true, if the numerator and denominator are both approaching 0, then the limit of your original fraction is equal to the limit of their derivatives. Notice we're not doing the quotient rule, so do not do the quotient rule here, but you simply differentiate the numerator, differentiate the denominator, and then try again, plug in c. So make sure numerator and denominator are approaching 0, and I should, just for completion, I should say or if this equals infinity, and it could be positive or negative, the sign of the infinity does not matter. And same thing here. So if it's 0 over 0 or infinity over infinity, then we can apply L'Hopital's rule and try the limit again. So there's the rule. It's actually very clean, very quick, and very nice. And let's look at a few examples. And these are actually the very first two that we originally did. And I am going to teach this from the perspective of an AP Calculus teacher. And currently, as of the year 2024, in free response situations, they have been kind of picky, and I say with good reason. They're trying to be mathematically sound about how you present your answer, and to justify that L'Hopital's rule, or to establish that L'Hopital's rule does apply, what they have wanted you to do lately is actually do the limit of the numerator and denominator separately. Now it's an added step, but you need to actually write down the limit as x approaches 4 of the numerator is 0. 4 squared minus 16 is 0. We need to write down that the limit as x approaches 4 of the denominator, x squared minus 5x plus 4, is also 0. Therefore, L'Hopital's rule applies. Therefore, and then I could say that the limit as x approaches 4 of my original fraction, x squared minus 16 over x squared minus 5x plus 4, is equal to, and one way that we commonly show that we're applying L'Hopital's rule is we'll put a small h above that equal sign, and that's say we're applying L'Hopital's rule. And L'Hopital's rule says that the original fraction, or the original function's limit, is equal to the limit of the derivatives of numerator and denominator. And keep in mind that we differentiate them separately. We're not quotient ruling this. So the derivative of x squared is 2x, and the derivative of the denominator would be 2x minus 5. And now we can substitute 4 in for the x's. 2 times 4 is 8. 2 times 4 minus 5 is 8 minus 5. That's 3. And we got the exact same answer we got through algebra. And so in this case, the algebraic method may be a little bit easier, especially knowing that we need to establish numerator and denominator separately or approaching 0. But in multiple choice, we can kind of skip some of the formality and jump straight to derivatives after establishing that we are in indeterminate form. And we get 8/3. So let's look at the other one. And this one, if you look at numerator and denominator, if you plug in infinity, so we have 3x plus 1. And I shouldn't say plug in infinity. You can't really plug in infinity because it's not a real number. But the numerator is approaching infinity. My denominator, x goes to infinity, is also approaching infinity. Infinity squared minus 9 would be infinity still. Therefore, we can apply L'Hopital's rule. This time I'm not going to write the original fraction. I'm just going to do the limit of the derivatives. The derivative of 3x plus 1 is 3. The derivative of x squared minus 9 is 2x. And here I only have x's in the denominator, so we're going to have a constant 3 over something infinitely large that will crash to 0, which again, if you know your rules about the degrees of the polynomials in numerator and denominator, that's a little bit faster. But L'Hopital's rule bails you out. That's a good thing. Is some people get those rules backwards. They'll forget when it's 0, or when you divide the coefficients, or when the limit doesn't exist. Well, L'Hopital's rule is a one-size-fits-all that kind of cleans that up for you. All right, let's look at a few more examples, and these are ones where you must use L'Hopital's rule. Some teachers teach some memorized limits, like number 4 is actually one that a lot of teachers will teach students early as a memorized fact. I don't do that. So I'm looking at this, and I would probably, before I start doing the limit of top and bottom separately, I would probably look at the top very quickly. E to the 0 minus 1 is 0. The denominator is approaching 0. So I can very quickly tell if L'Hopital's rule is needed, and it is. So I'm going to go ahead and establish that through the formality of saying the limit as x approaches 0 of e to the x minus 1 is 0. The limit as x approaches 0 of x would also be 0. Therefore, we can apply L'Hopital's rule, and the original limit would be the limit of their derivatives. The derivative of e to the x minus 1 is e to the x. The derivative of x is 1. And if you plug in 0 for the remaining x, we have e to the 0 over 1, which is indeed 1. So there's that one. And that's an example of one where you had to use L'Hopital's rule. There's no algebra you're going to be able to use to clean that up into something that cancels on top and bottom. So let's look at number 4. Sine of 0 is 0. The denominator is 0. Let's go ahead and establish that more formally by saying the limit as x approaches 0 of the numerator, sine x, is equal to 0. The limit as x approaches 0 of the denominator, which is just x, will also be 0. Therefore, I'm going to write the limit as x goes to 0 of the original function would equal the limit of their derivatives. The derivative of sine x is cosine x. The derivative of x is 1. And now I will plug in 0. Cosine of 0 is 1 divided by 1. And we get a final answer of 1. And so you see L'Hopital's rule, once you establish your numerator and denominator are approaching 0, it's pretty clean. It's very nice and it's very efficient. So let's see, what else? I think I have 2 more that I wanted to look at. So let's check this one out. And I am going to intentionally do this incorrectly in the eyes of an AP reader just to try to explain why we don't do this. So if you plugged in 4 cubed minus 64 is 0. If you plug in 4 here, 4 squared, oh, wait a second. 4 squared minus 9, well, that's 16, that's 7. Well, shoot, that's not even indeterminate form. That's why you always plug in first. That's 0. Now that I've worked that out, I remember doing that on purpose. So that ends up being 0 over 7, which is just 0, and L'Hopital's rule is not needed. And you always, always, always want to establish that we have indeterminate form before you dive into derivatives, because in this example, if I did just dive straight into L'Hopital's rule without establishing that it was indeterminate. So let's pretend maybe this is a multiple choice question where you don't really have to show immaculate work. Some students may think, well, I'll just cut out a step and I'll get straight to the derivatives. Well, if you do that, you would have 3x squared over 2x. 3 times 4 squared is 48. 2 times 4 is 8. And you would incorrectly get an answer of 6, and it would not surprise me if in a multiple choice situation they would have 6 as one of the options, because they know some students might just dive into L'Hopital's rule without verifying the indeterminate form. So that one's gone. So I think what I'm going to do, I'm going to go back to this problem right here, number 4, and I'm going to hide this. And let's pretend we didn't do that. And let's say that I wanted to, in a free response situation, I'm going to plug in 0. And I said sine of 0 is 0, and 0 is 0. And I write that this limit is equal to 0 over 0. Okay, so in my mind, I'm thinking that's indeterminate. You can't have 0 over 0. So then I go down to L'Hopital's rule, and therefore this will equal the cosine of x over 1, which ultimately ends up being 1. Well, what I've done here is I've created, in essence, what we call a linkage error. I have declared that this limit is equal to 2 different things. I have said up here that the answer is 0 divided by 0, and I later said down here that the answer is 1. And by saying both of those things, I've unintentionally made the declaration that 0 divided by 0 must be equal to 1. Okay, well, that's not true. Well, first, this is not actually 0 over 0. This is something that is close to 0 over something close to 0. Second, in this case, the indeterminate 0 over 0 did clean up to 1, but we had an example right here where the indeterminate 0 over 0 ended up being 8/3. It doesn't have to equal 1. And so you'd never, ever, ever write equals 0 over 0 because you inadvertently create that linkage error, even if the L'Hopital's rule is applied correctly. You want to make sure that you are showing with correct math that the numerator and denominator independently do approach 0. Therefore, we can apply L'Hopital's rule to finish the problem. Okay, so I have, I think, one more. Yep, number 6 is the last one. And so let's check this guy out. And I think this is going to be an interesting one. I'm going to look at the numerator, limit as x approaches 0 of sine x minus x. And that's sine of 0 minus 0. That's 0. Let's look at the denominator. X approaches 0 at 5x squared. Well, that's 0. Therefore, I can apply L'Hopital's rule. And, excuse me. And the limit as x approaches 0, we will do the derivative of top and bottom. The derivative of sine x is cosine x. The derivative of x is 1. And the derivative of 5x squared is 10x. And I'm looking at this, and in my mind, I can see that the numerator and denominator both approach 0 again. That's 0, and that's 0. Well, that just means I need to keep going. We can do another round of L'Hopital's rule, and we keep going until we escape the indeterminate form. So this is a little bit of an evil problem because now, because I'm about to use L'Hopital's rule, I have to establish numerator and denominator approach to 0 independently. So I once again, limit as x approaches 0, cosine of x minus 1, cosine of 0 minus 1 is 0. Check out that denominator. X approaches 0 of 10x. Well, 10 times 0 is 0. Therefore, once again, we can apply L'Hopital's rule. Therefore, we will have the limit as x goes to 0 of the derivative of cosine x minus 1, that's negative sine x, over the derivative of 10x, which is 10. And finally, I'm out of indeterminate form because I have a 10 in the denominator. In the numerator, I have negative sine of 0. Sine of 0 is 0. So we get the very unsatisfying answer of 0 in the end. I don't know why. I just don't like it when I do all that work and I get 0. I want something more fulfilling. But there's your answer. And it is possible to need to do L'Hopital's rule through multiple iterations. And as long as your answer is an indeterminate form, then you are to just keep going until you finally escape the indeterminate form. Hopefully this makes some sense to you. Thank you very much.